to Module 49 on LSTMs, long short-term memory, GRUs, gated recurrent units, and gated RNN variants. So by the end of this module, you ought to be able to explain the role of the different small components of an LSTM neural network. An LSTM is a type of RNN, but it's a little bit more complicated than we've seen. You ought to be able to explain the role of each of the new components within it. You should be able to derive how the LSTM cell state, which I'll introduce in a moment, provides this additive pathway for gradients and for remembering information over a long period of time. You should be able to compare LSTM and GRU architectures, both of which will be introduced. This includes things like parameter counts, gating structures, empirical trade-offs. You should be able to implement these in PyTorch and diagnose what we just mentioned in point 3, and to some extent at least justify, explain your choice between RNNs, which we saw in the previous module, and either of LSTMs and GRU, which we're going to introduce today. So this is another representation that we've seen, another representation of an RNN, which is a model we saw previously. It comes from this link, so click on this link to see a little kind of tutorial blog post on recurrent neural networks and the kinds of RNNs we're going to see today. So this is where the visual comes from. And it's just it kind of just blows up the hidden layer a little bit. So we still have X's, or inputs, coming into the layer in which we're looking at right now. And we have a combination here. So we have kind of a concatenation in these two paths of the information at time x sub t and the hidden layer at time h sub t minus 1, at time t minus 1. These are both combined together. They're through weighting. And then there's a nonlinearity. In this case, it's a tan h. And then this new hidden layer at time t, h sub t, is either passed deeper into the network towards the output. So over here we have the hidden layer serving as the input to the next layer in a deep model. And then it's passed forward in time over here. So it's kind of copied in both of these areas. So this is essentially the same model we saw before. It's just kind of zooming in to this hidden component. So in the vanilla RNN, this hidden state h sub t, which is a big H dimensional vector of real values, has to serve several purposes. It has to remember anything from the past that might be useful later. So we kind of talked about how this hidden vector is accumulating information in some sort of magic way, pseudo-magic, I guess. So it has to remember anything that might be useful later. How it learns to accomplish this happens naturally through backpropagation, but it does happen. And we saw examples of how this actually is helpful to us in the examples we had in the previous module. That being said, these vectors are fixed length. They can't remember an infinite amount of information. To some extent, you have to compress information out or lose information when you're continuously, feeding information forwards in time. So these hidden vectors have to some extent, forget things that are no longer relevant and learn how to do so. That's the second point. And the third point for this vanilla RNN is that they have to also represent the current input well enough, because they have to, make a decision now, for example, or they have to, just incorporate information from the current x sub t into its internal representation for further processing later. We saw a couple of architectures of RNNs previously. Some of them were many-to-many, so maybe you have to make a decision, a classification, or a regression, like at y sub t, or you just have to incorporate information and have it be used later for a classification at the end of the entire sequence in a many-to-one sort of scenario. Either way, this fixed length vector has to, incorporate the dynamics of time. It has to forget things in the past that might not be useful for it in the present or future, and it also has to continuously incorporate what it reads at every moment in time t. Now, unfortunately, not only is it difficult to compress information in a restricted space like this, but these goals can conflict. If your recurrent weights of W sub HH, the recurrent weights of the hidden layer back into itself, which is essentially this component over here in this diagram. If it's tuned to preserve old information, then the gradient of the current prediction with respect to the parameters gets diluted. So it ends up kind of focusing too much on the past and not so much on the present, which is also true of a lot of us humanoids in real life. And if WHH is too tuned to the current responsiveness, it's too reactive. If too much information is written into H sub t from the current moment's observation, then it becomes highly reactive. Old information is overwritten. You don't learn from the past. This is also an unfortunate cognitive bias of human beings. I'm anthropomorphizing quite a bit, but this is technically a problem of these RNNs. If too much information comes from the past, that's a problem. If too much information comes from the present, that's a problem. You want to have balance, but you can't just have balance automatically. Often in practice, these two sub-goals are in conflict with one another. So the key question that leads us into today's module is, can we separate out long-term memory from short-term working representations? Can we balance these two sub-goals effectively? And surprise, surprise, the answer is going to be yes. If we just have separate variables that can have different update rules that allow us to balance these two sub-goals. So introducing the long short-term memory, or LSTM. In fact, this was introduced quite a while ago in the late 90s. But it became popular in the mid-2000s and even in the early 2010s, I'd estimate, in the fields of natural language processing to solve a variety of tasks. The main kind of innovation here is the introduction of this cell state, which we call C sub t, C for cell. And it's a new vector that runs in parallel to our hidden state. We still have the hidden state. The hidden state still performs the same function as it did before. It's still going to incorporate the dynamics of time. It's still going to incorporate information from the current observation, x sub t. So we see that kind of in this diagram over here of the LSTM. But we also have this other vector, C sub t, which kind of rides along the top of this diagram. We see it kind of zoomed in over here. Same kind of idea happens. We have a cell state at time t minus 1. We make some modifications to it, and then we pass it forward in time from time t forward to the next moment in time. This is going to serve as sort of, you can think of it in the Turing kind of terms, in terms of like a tape that is written like by a machine, like information is written, it's retrieved from it. It's a storage mechanism. Others like thinking of it as a hard drive that you can decide to write information to. You save information to, you read information from. Whatever metaphor works for you. This cell state is meant to explicitly hold information for long periods of time. And there's reading and writing processes on it. So that's why I like thinking of it in the Turing theoretical sense. So we still have, just to describe our variables here. C sub t, this vector of real valued numbers at the top, is going to be our long-term memory. Another analogy is it's a conveyor belt running along the sequence, and we can decide to remove information and write information to this conveyor belt that's then passed along in time. H sub t will serve the same purpose as before, but it's going to be more explicitly for short-term information and output representations that are passed upwards through the neural network. So a recurrent neural network can also have multiple layers. Here's one layer of the recurrent neural network. There's another layer on top of this that's also passing information forward in time. H sub t at this particular layer can be input as the x sub t to the next layer above it. Right, just like we saw many times before. And it turns out that this is practically good, because the way RNNs work is that they suffer a little bit practically from overwriting information from whatever observation comes in. So it's basically for short-term memory. It passes information up through the neural network, so representations that can be useful for more abstract representations deeper in the network. H sub t is all good at that. F sub t, this is a gate. So I'll go through the gates in a moment. But we have these mechanisms I'm pointing to here with my mouse, where we decide to remove information from the so-called conveyor belt, from the cell state C sub t. This is the forget gate. This is a gate where we decide this information is no longer necessary. Call it F sub t. I sub t is information to write to the gate. This is where we add information to the conveyor belt as it moves along. And that's more or less it. The output gate is what we pass up through the neural network like we have before. So we're going to see this in a sequence of steps in a moment. I'm going to mention that these gates are going to be basically sigmoid functions. They're going to go from 0 to 1, and they're going to be multiplicative. And just like any 0 to 1 function, if you multiply its input or rather, if you think of this gate as a 0 to 1 function, you multiply that function by some other factor. If it's close to 0, it tends to zero out that information in that factor. If it's close to 1, it passes it through. You can think of this as sort of a filter. It can also not necessarily like deterministically turn on and off information. Like I think sometimes I'm referring it to that way, like we're removing information from this conveyor belt C sub t or adding information to the conveyor belt C sub t. It's usually not that deterministic or discrete. Because this is a sigmoid, it's on a range, and you can like add and remove information, so to speak, in a fuzzy way. It's not it's not a binary operation, but it's a smooth operation. Let's like the song. So F sub t, like close to 0 means erasing, close to 1 means keeping in the filter sort of metaphor. But like just like everything else in machine learning, it's not really as simple as all that. So we have this combined vector, this concatenation of h sub t minus 1. This is the hidden vector from the previous point in time, and the observation or the input at time t, which is x sub t. This concatenation is shown down here in the bottom of this graph. This is going to be a real valued vector with size big H plus d, where big H is the size of the hidden layer and d is the size of the inputs. So the forget gate, which is this f sub t over here, is basically a sigmoid function taking a weighted combination of the previous hidden vector and the input vector and a bias. So this is the same old sort of linear combination we've seen countless times before. This is very similar to the regression model we saw at the beginning of this course. W sub f is learnable, and B sub f is also learnable. And it produces this sigmoid function, which basically over the size of C sub t, the cell state, decides to kind of accentuate or at least pass through information at certain elements of that cell state and de-emphasize or bring down to 0, towards 0 anyway, other information. So this essentially is called the forget gate because it decides what in the cell state do I want to forget. And you can, all these images come from this link that I'm just linking consistently down here. The input gate says, we've obtained new information, whatever happened at x sub t, speaking anthropomorphically again. I want to combine it with the short-term context I get from h sub t minus 1. I'm going to pass this through a sigmoid function. So it's the same kind of operation we saw a moment ago in the forget gate. We still have a learned parameters w sub I and the bias b sub I. But in this case, we're learning like what areas of C to write to. And this is called the input gate. So it's basically, it's still a sigmoid function, so it still goes from 1 to 0. It's still kind of a filter on the cell state, and it's just basically choosing which elements of the cell state am I going to write to. I'm not writing anything quite yet with I sub t. I'm just deciding what areas of the cell state I want to write to. I'm going to write to there, there, and there. I'm speaking very anthropomorphically, obviously, but hopefully that helps to convey the idea. The candidate cell is this C tilde sub t. This is the information I do want to write. So I have information from the short term, from h sub t minus 1, from the current observation x sub t. This is also passed into a tanh function. There's other learnable weights, so I still have weights w sub c and b sub c. These are also learnable weights kind of shown down here in this little arrow. This is passed through nonlinearity. Here it's a tanh, but it doesn't have to be. And then this produces the information that I'm going to write to the cell state. The writing actually happens here in a couple of operations. So the first thing I do is I multiply the old cell state at time t-1 with the forget filter f sub t. This is where the actual forgetting happens. So the forget gate, the sigmoid function decided what information can stay. It's close to 1. What information is 0? It's close to, what information has to go away? It's close to 0. And again, this you have a cell state, which is a vector, and you can think of weightings applied to every element of that vector. And then multiplying these things together actually de-accentuates some elements and essentially passes through the others in this cell state. Then I take the input vector I sub t. These are the elements I say I want to write to here, 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 and here. And c tilde sub t is the information I actually write. And that this is all determined by these weight matrices and biases that we passed into these sigmoid functions respectively. And you multiply them together. So again, I sub t is sort of serving the inverse purpose of f sub t. It's not de-accentuating elements of c sub t. It's deciding this is where I want to write to c sub t, and then it fills that information with c tilde sub t. And then you just add these together with the cell state. So this is where the information is written. These overlap. And then you have the output. Again, x sub t and h sub t-1 is passed through a sigmoid function. W sub o and b sub o are yet more parameters that you can learn that decides what information do I want to propagate forward. So when I propagate information forward, I can make use of the cell state. So here the information from the newly updated cell state is passed through another nonlinearity, in this case a tanh, that is multiplied with whatever I have from my previous hidden state and my current state, a current observation. This is all combined together into the new hidden state h sub t, which I push forward as my short-term memory forward in time and upward through the network into deeper and deeper, more abstract layers above me. I'm doing an awful lot of things here, but there's only a small number of gates where we're actually performing. So we forget what we want to choose, what to forget. We choose where we want to write. We choose what we want to write, and then we combine everything together. And that's basically it. So here I'm just explaining a little bit of what these operations are. These stars here are kind of element-wise products. Here it's written as this sort of dot with a circle around it. These are all the same concept. I think I pointed out in a previous module that this asterisk technically is a convolution operator, so they shouldn't have used this operator if you want to be pedantic and therefore correct about it, but it says maybe. So it's simple in some sense, but it's also complicated. We've introduced all of these new weight matrices. We've introduced the weight matrix for the forget gate, the input gate, the context vector, candidate vector for the context, and the output vector. So we have these 4 components. We have all these new weight matrices we have to learn. So having more parameters you have to learn comes with its own kind of baggage that we've talked about a lot previously. I'm going to get to another kind of criticism of LSTMs in a moment. I don't want to burden you too much with introducing you all these new ideas and suddenly telling you where the problems are. But for now, this seems to solve a bit of a problem that we saw with vanilla RNNs, right? Where you had a single vector to serve all of these different purposes, and now we have parallel streams, one of which is focused on long-term memory, and we decide what we want to store in long-term memory with this kind of cool mechanism. And we have the short-term memory h sub t, which understands the current context, and that's used for the deep representation up towards the output of the network. So we have all of these new weight matrices, and speaking kind of a little bit loosely here, because each of these will have the shape h multiplied by h sub plus d. The new parameter count is 4 times h plus d plus 4h, which is on the order of 4 times vanilla RNN. So all of this new capability and these problems we've theoretically solved, so far only theoretically, come at the cost of 4 times more parameters, which again has challenges. So like a couple of quick pseudo side notes. Why is the cell state a gradient highway or a conveyor belt? So the cell state is additive in C sub t minus 1. So basically, this is from the previous slide. I'm not introducing any more information here. We have the old information at time t minus 1. We scale it by this forget gate, and then we explicitly add new information to it with this input times candidate right. So we're explicitly having these two operations. If we can take the partial derivative of C sub t with respect to the previous cell state, for reasons I'm skipping over right now, we get a diagonal matrix in F sub t. So when F sub t is approximately 1, we talked about this being sort of like a filter. The forget gate is open. The gradient flow will go back through C sub t with basically no shrinkage. If we're just passing information forward in time along C, from time t minus 1 to t plus 1 and so on, and the forget gates are open all the time, then the gradient, we're going to flow back through the network, is going to just flow all the way through. And that's what this little equation here tells us. We can compare this to the vanilla RNN. We touched briefly on the Jacobians of the vanilla RNN in the previous module, where the diagonal had more or less this form, where it was the diagonal of 1 minus the hidden state at time t minus 1 squared times the weight matrix. This involves a full matrix multiplication at every step. So the multiplications are computational, a bit more expensive than what we have over here. So we're adding a lot of new parameters we have to learn, but these differentials tend to be pretty efficient, leading people to, I guess, to refer to this as a highway as opposed to a slow-moving conveyor belt. So it helps. Also, we talked a lot about how like multiplying lots of gradients with each other over a long period of time can introduce the risk of having gradient explosions or gradient vanishing, and that isn't so much the case when you're doing something additive like this, when the partial differentials are simple. That problem vanishes, so to speak. It goes away anyway, and so this cell state is sort of a persistent memory. So I like when I learned the concept of an LSTM, I learned it sort of in with the metaphor of having a hard drive that you can choose to write to, and I think that makes sense in this context as well. So the cell state can be like a near identity gradient path when the forget gate is near 1. We like the gradient path to be near identity in terms of its norm, so that's great. The model itself will learn when to open and close this path, so we're not going to hard code it. Like again, just like so much else in machine learning, it'll handle anything on its own if you give it enough data and if you set up your empirical scaffolds appropriately. So all good. A bit of a side note here, we also want to talk a little bit about the gradient flow in a bit more detail. So for the loss at the very end of the final step t, wherever it is, but you can assume it's at a many to 1 RNN, the gradient with respect to the cell state at time t will be, again, using the chain rule, will be the gradient of the loss with respect to c sub t times the product of k going from t plus 1, the next time step, all the way to time t. And all these diagonals that we just defined in the previous slide is all we need to define the gradient through the network. And this diagonal is on the forget gate. So because every factor is diagonal and element-wise bounded by 0 to 1, then when the forget gate is approximately 1 for all k over the periods in time from now-ish to the end of the time sequence, the jth gradient component will survive all of these big T to time t steps undiluted, which is nice. When the f sub k is close to 0, which is to say that the forget gate decides to forget information and decides to filter like whatever information comes to the cell state from t minus 1, we're going to forget it, so it's going to set its output close to 0. For some k, then the jth gradient will be intentionally removed, and the network will decide this memory slot is irrelevant, so there's no need to carry it forward. And again, this is contrasted with the vanilla RNN, which we defined in a previous module, and we mentioned a moment ago has this multiplication between a slightly more complicated diagonal and the weight matrix. from H to itself. Every factor will have these full matrices, powers of these matrices with spectral radiuses, or these norms that are much smaller than 1 will shrink and will end up having gradient vanishing, which we don't like. So LSTMs replace these full matrix products with element-wise products, which are more controllable, and this is the core reason why LSTMs can learn dependencies over long periods of time, where vanilla RNNs cannot. And we're going to see this empirically. Vanilla RNNs are far better at learning time sequences than MLPs are, and we saw that empirically in the previous module, but LSTMs can remember information over long periods of time, hence the name long short-term memory. So theoretically, so far we're good. We have a theoretical idea of all these gates and mechanisms that can store long-term information. We've demonstrated in a very superficial sketch why this is the case and why information can survive long periods of time without the vanishing gradient problem occurring. And superficially, it's mostly due to the simplicity of the gradients that we're multiplying together as we move backwards through a network. I should mention right now that LSTMs are also considered RNNs. So the big field of RNNs include vanilla RNNs, like we saw previously, and LSTMs, and at least one other network, which I'm going to introduce, which solves some of the problems that LSTMs have. Here it is, that very network. So this is the gated recurrent unit, or GRU, another kind of recurrent neural network. Introduced by this paper, which I'd really recommend you check out. It simplifies LSTMs a little bit. So one criticism of LSTMs that I didn't mention when I was walking through all of the gates, and you might have intuitively realized when you were looking through these slides or when you were listening, is that there's all these independent separate components that all have to kind of come together naturally to cooperate or coordinate with one another. But we are learning all these weight matrices, all these 4 new weight matrices that I introduced before. Each of these are going to be trained with gradient descent somewhat independently of one another. And ideally, if we get enough data and if everything's set up appropriately, then the forget gate will, the forget weight will learn how to turn off specific elements in the cell state. It'll turn off elements I, J, and K of the cell state. The input will learn that it wants to write to elements I, J, and K, because that makes sense. We want to remove information from the previous cell state and replace it with new information given this new observation we just had at X sub t. So this is kind of a coordination going on, right? But there's no explicit requirement that the forget gate and the input gate are collaborating that closely. So it's possible that the forget gate could learn, through learning, could decide, so to speak, to turn off a completely different set of elements of the cell state than the input vector decides to write over, right? So you can be in a situation where we've forgotten information because of the forget gate, but we haven't replaced it with new information with the input gate. And that would be a problem, probably, right? Or at least it wouldn't theoretically serve the purpose of these gates and of the cell state itself. And, just a bit more practically, introducing all of these weight matrices also just comes with a computational cost. So the gated recurrent unit solves these problems by going back to having one single vector representing everything, representing both the long-term information and the short-term information. But it kind of takes inspiration from LSTMs to decide what to write, but it does so in a much more coordinated way. So we're going to have this reset gate, which decides to reset certain information from the hidden state. We have an update gate over here, which decides to write information to the hidden state. We have the candidate hidden state, which comes out of this update gate. This is very similar to the input and candidate gate from LSTMs. And then we have the hidden update, which occurs over here on the right. And this writes information back to the hidden state. And then this is passed forward in time and up through the network towards the output. So we've simplified a little bit. We're still requiring on some coordination between the reset gate and the update gate. But in all these cases, we're operating on a single vector, and we can still decide to keep information and turn off other information. So we still get the theoretical benefits of, or the theoretical purpose of the LSTM, but we do it in a more computationally efficient way and in a way that doesn't require too much magical coordination happening through luck. So these gates, this reset gate R sub t decides how much of the past hidden state the candidate should see, and R sub t being close to 0 forces H sub t to ignore information in the past, so it filters information out. This is still sigmoid, so all of these sigmas over here represent sigmoid functions from 0 to 1. The update gate will kind of interpolate between the old hidden state and the new candidate, so it'll decide to carry old information and write new information, and it can learn to do both of these things at the same time effectively, in a way that we don't get kind of by chance, in a way that's more coordinated and learned than simply through accident like we had with vanilla RNNs. So we have fewer gates to learn, fewer weight matrices we have to learn. We have R, Z, and H now. So now we have 3 times H plus D plus 3H. These 3H's are all the bias terms. So we have still more parameters we have to learn than a vanilla RNN, but we have only about 75% of the parameters we have to learn that an LSTM has to learn. So we're less likely to run into issues related to overfitting, for example. So like what variables do these 3 kinds of RNNs have? Well, the RNN just had H sub t. GRU still has H sub t, although the way it's updated is different than the vanilla RNN. And an LSTM has both H sub t and C sub t kind of running in parallel with one another. Vanilla RNNs have no gates. Everything is just trained through simple backpropagation. GRUs and LSTMs have gates, these sigmoid functions that can decide what to reset or what to update, or what to forget input and output respectively. We have these parameter functions which we defined earlier. Now, the claim I'm making is that the vanilla RNN will not be able to remember very long-term information because information will vanish, either through lots of updates through inference, through the forward pass, or we won't be able to learn information because of vanishing gradient problems as we push information backwards through the network during training. But a GRU and an LSTM will be able to have long-term information through explicitly learning to keep and update particular information. So in general, we might want vanilla RNNs can still be useful for short sequences. Generally, LSTMs might be helpful for long sequences or tasks that require fine-grained control with regards to information control. But GRUs might have that same benefit but at greater efficiency compared to an LSTM. So a bit of a rule of thumb is that if you're thinking of implementing an RNN of any kind, and you kind of have to do an RNN, an LSTM might be a good place to start. But if training matters, go ahead and use a GRU. RNNs are used sometimes, especially in different disciplines, but you may not have heard of GRUs. But that's sort of the rule of thumb. My rule of thumb is usually to start with GRUs. In my personal experience, anecdotally, GRUs tend to not only be faster, but tend to be more performant and generalize better than LSTMs. So I would say, even though the rule of thumb sometimes says start with an LSTM, and a lot of research papers use LSTMs as the benchmark baseline, I would recommend GRUs if possible. Here's one of our anti-examples. This is a bit of a stretch case. I don't necessarily agree with it, but it's possible. So here we go. Imagine your task is to classify a simple 3-word like product titles. So you have a name of a product, and you wanted to say, is this electronics or is it clothing, or is it something else? These sequences are short. There's no long-term information that you need. So the whole purpose of having long-term memory disappears. So reaching for an LSTM right off the bat might end up giving you worse validation accuracy than a simple RNN because you've over-parameterized a model given a small sequence that you can learn that results in overfitting. It doesn't generalize well. You've you've fallen into the trap of machine learning of reaching for something that seems fancy but doesn't actually serve the purpose as well as a simpler model. So indeed, you have unnecessary complexity. LSTMs have 4 times the parameters of vanilla RNNs. And you just didn't need that given the nature of the data. You'll have slower convergence, so it takes longer to train. More parameters mean more gradient updates before all these gates and other subcomponents of an LSTM settle on their eventual configurations. And also it'll lead to like a misunderstanding of the results. If the student, this amateur student, does the experiment, they might learn that, oh, like RNNs are better than LSTMs. I did an experiment with these titles of products, and RNNs are better. Therefore, not having looked into why this could happen or not deciding to learn anything any deeper than this, they'll carry forward the misapprehension that RNNs are just better than LSTMs, which is not in general the case. So like I keep on trying to emphasize, it's always good to do as many experiments as you can and understand the nuances a bit better. So the main takeaway from this anti-example is try to match the architectural complexity to the task. If it's a simple task, a simple model will tend to not only suffice, but in some cases even do better than the more complicated models. Indeed, yeah, for my suggestion is for small sequences, a well-regularized vanilla RNN can do better than other methods. Under the surface here is maybe you don't even need an RNN. If you only have 3-word product titles, then maybe you could go back to a simple window approach in an MLP and cut out the recurrence altogether, and because you're basically just classifying labels anyway. So maybe RNNs aren't even necessary in this anti-example. And again, if you have the opportunity, I'd always recommend doing the experiment and figuring it out that way. So a couple of worked examples. So in the previous module, I showed how vanilla RNNs can retrieve the seed value, like this, the value at x sub 0 from 30 steps compared to a windowed MLP. And we won, right? So vanilla RNNs did do better, and were able to solve that problem. But what if we went to longer term memory, right? So what if we went back to 100 steps instead of 30 steps? Same task, the only thing that's changing here is the value of big T, okay? So this is a clean kind of cartoon toy example. There's one relevant time step, it's the one at time 0. It's very controllable, there's no ambiguity with regards to the labels, and we ought to be able to have a model that can generalize what it's learned. It says I need to remember x sub 0, and I need to remember it for as long as possible, whether it's 30 steps or 100 steps, and I need to not overwrite it. There is a theoretical noise floor. So in module 48, we introduced a little bit of theory in terms of the worst possible performance for an MLP or any model that can see step 0. This will be approximately 0.083. And then we're going to compare 3 models with the same hidden state size. Vanilla RNN is going to be our baseline, and then we're going to look at an LSTM and a GRU. Here's the code that just generates the time sequence. We're going to generate 3,000 training samples, and everything else is exactly as it was in lesson 48. Here's a few of the random walks over 100 steps. You can see where they start over here at time x equals 0, and you can see where they end up. And again, it's just a control theoretic problem where we're adding a bit of noise at every time step. So again, maybe I skipped a little bit. Yeah, so we're going to use Torch again, as you do. So we're going to use CUDA, again, push it to whatever device. We're going to push to CUDA if we can, otherwise we're going to use a CPU. We're using the loaders from Torch. Our hidden size is 32. We create our sequence models. We have RNN, which is our vanilla RNN from PyTorch. We have LSTM, which is our LSTM model from PyTorch. And we have our GRU, which is our GRU model from PyTorch. And we can define each of them. We define them with our input size, which is just 1. It's a scalar variable we're tracking. We have our hidden size, which we obtain from our hyperparameter. We have a linear head on the end of it, like we talked about quite a lot, in terms of we want to classify it, or we want to do a regression or a classification at the end of this. So we slap a head on it with a linear output, and then we're good. We have a method to counter parameters as always, and as I suggested earlier, the LSTM is approximately 4 times as many parameters as the RNN, and the GRU is about 3 times as many parameters as the RNN. Here's where we do our training. I keep on saying I don't want to repeat myself, so I'm not going to, but all of the regular aspects of using PyTorch for doing training comes up. We have our optimizer, our loss function, the number of epochs we are allowed to run, our batches, the necessary zero gradients, zeroing out of the gradients at every batch, and pushing all of the batches to our device. I was going to run this a bit longer, so initially, I guess this is just a side note, I was running epochs for 120 iterations. I needed to, for these slides, I needed to cut things down a little bit, so I made it a bit shorter, but you can go ahead and run this for many more runs than, like epochs than 120, training epochs. And then at the end of this, we just maintain our histories in terms of our training MSEs and our validation MSEs. And here they are. So here we have the naive floor shown here in red dash. We have the noise floor caused from the control theoretic process. This is the purple dashed line. And then we can see in green, orange, and red, the GRU, the LSTM, sorry, green, orange, and blue. I'm not sure what happened. The GRU, LSTM, and RNN, respectively. Their losses, mean squared error, over the epochs of training. I mean, you can go for longer. I think there's a bit of dynamic change after 60 epochs, but the trends generally are going to continue here. And you can see right away that GRUs are far and away the winner. LSTMs and RNNs actually end up being kind of close after 60 epochs. Again, I think things diverge if you keep on going after a while. So LSTMs are going to be better at retaining information over 100 time steps, but GRUs are accomplishing the task of these gated RNNs that we're introducing in today's module by having far superior losses over the epochs. I'll make a quick point here that in solid curves are the training, and the dashed ones are training, and the solid ones are a validation. Just to compare them against each other, just to see if there's any overfitting going on. And for example, in the GRU down here, you can see the loss for the training in the light dashed curve, and the loss for the validation in the dark solid curve. Kind of track each other very nicely. So there doesn't seem to be anything untoward going on. And so far, so good. Things look satisfying. This is just a bit of a report. So the RNN ends up with a final MSE, which is about 0.08. The LSTM is a little bit better than it, but the GRU greatly beats both of them. This is after 120 iterations, actually. So the final MSE is good. The native floor is only beat by the GRU, and actually the GRU busts through the noise floor also, so it's extremely accurate. That's all there is to say. We've demonstrated that at least one of those two new models we've introduced does indeed retain very long-term information in a way that the vanilla RNN cannot, at least in this toy example. Let's get to some real-world, like real data. Here we have a Stanford sentiment tree bank, SST2, which is one of the popular standard data sets used to measure sentiment, the positivity or the negativity of text, actual real text, in this case, movie review snippets. We're going to use only a 2,000 example subset for the purposes of the slides. The average review length will be about 20 tokens. A token is like a type of word, like the usage of a word. This is moderate. Like 20 tokens is pretty short. It's not trivially short. It's longer than a title, but it's not really that long either. This is approximately 5,000 words. We're going to compute the number of words in a moment, and we're going to assume 30 token padded sequences were necessary. So indeed, this sentiment, telling whether or not a review is positive or negative, requires information that can span a range that's normally outside of a small window, and it can span over an entire sequence. So someone saying, the movie was pretty good at first, but at the end I didn't like it, or this movie is fundamentally flawed, but considering the acting and the writing and the directing, it was generally an enjoyable movie, right? So there's bits of information about the sentiment at the beginning and end of those example sentences, and to come up with an overall classification for the sentiment, positive or negative, you're going to have to incorporate information that spans a long period of time. So long-term dependencies are real. They're by no means extreme. This is a good test of long-term dependencies, which for a long time was a pernicious challenge in natural language processing. So we're going to again compare vanilla RNNs with LSTMs and GRUs on the accuracy of classifying positive and negative sentiment from these input texts. So we're going to have to load it up. Here, SST comes from data sets, which is from Hugging Face. So we're introducing a bit of Hugging Face, which is also a very common library in machine learning. So go ahead and pip install datasets if you don't have it already. It has this load dataset function, which allows us to load the Stanford NLP SST dataset. We're just going to grab the training dataset in this case. There's a lot of other things going on here. Here's where I set all my seeds to be the magic number 3151. We tokenize. We pad. There's a lot going on here which is beyond the scope of this class. Like you don't need to know what unknown word means. That's going to be for your classes on natural language processing. At the end of this code, we also use data loaders, like as usual. We have a training and validation. We have 4,000 training data points, 1,000 validation data points. So we have our sentiment model. We get our embeddings. I think I've skipped over before. I'll go back here now. This is again outside of the scope of this class technically, but just so to make sure you understand. Actually, I think I might introduce it later. Where is it? Yeah. So this data comes like the text has already been transformed into these vectors for us, so we don't need to encode them ourselves. So every word is represented by a embedding of numbers, just like we saw earlier with word2vec and glove in the earlier representation learning slides on representation learning and natural language processing. The same idea here. Our inputs have already been transformed into embeddings for us. So we're not given the raw text, we're given embeddings for every single word we see. So we already know, again, I'm skipping over a lot of stuff here for the purposes of this class and the context. We have a vocabulary size, we know how many words we can potentially see. We have an embedding dimension, which is that vector I mentioned a second ago, which takes a word and casts it into a representation vector. These are our inputs into the neural network. Here it is. We have our different kind of classifiers. One's an RNN, one's an LSTM, one's a GRU. And we apply dropout. We didn't do that in the previous example because we didn't really need to, because we had a simple toy example, but we might need to regularize a little bit here. So we're applying dropout. We have our linear head on top of our RNN to do eventual classification. And that's it. We also specify what type we're dealing with. Is it RNN, LSTM, or GRU? And everything else is normal. We have our 3 models for each of RNN, LSTM, GRU. We send our model to the device that we obtained from the call to torch earlier to see if we had CUDA or not. In this case, the RNNs, LSTMs, and GRUs have very similar parameterizations compared to the previous example. Just FYI, everything's going to be more or less equivalent in terms of the parameter counts here. Again, the same basic process as always in terms of our optimization, our loss functions, our batching, and so on. We train our system and we maintain a history of it. And here's the results of the training over only 10 epochs. I'm going to make sure this is, obviously this is all the same Yeah, so I changed this to 10 epochs just for my own sake when I was producing these slides, but you might want to go a bit longer than this. Um, these training dynamics do change a little bit later. Just like in the previous example, it looks as though um, uh, some of our models one of our models is going to be similar to the baseline performance. Previously, the LSTM and the vanilla RNN were performing similarly. Here, it's the GRU and the RNN, which are performing similarly in terms of accuracies and cross entropy loss, respectively. But they're going to diverge if you keep on training for longer. Regardless, we have our chance floor. Like in this case, it's only positive and negative, so the silliest baseline possible will be 50%. Not knowing anything about the distributions in terms of how many positives or negatives actually occur in your training and validation sets. But you can see the LSTM is kind of quickly, after several epochs, getting far better performance in terms of accuracy. It's kind of starting to run away with it. And indeed, its validation loss is also dropping quite a bit. This is why I say you might want to, when you download this code and run it yourself, try it for 20 or 30 or 40 epochs to see when this validation loss will actually kind of taper off. Because it looks like we haven't achieved our optimum by any means so far. You might notice also that not all of these lines end at the same point. We applied early stopping here to the training process. Here. So lines 30 to line 36 is where we sort of decide whether or not we want to continue or not. If the validation loss on average is less than the best validation loss we've obtained, and so on, and we've passed over like a certain, we have a patience. We're allowed doing worse than our best for a little while, but if we're consistently worse than our best and we've exceeded our patience, then we stop the training process. That's why I didn't have to do that, but we do that a lot in training deep neural networks, and it also saved my computer a little bit of time. Anyway, you don't need that. You can cut out that little block, and then RNNs would also keep on moving forward in the future. But when I didn't have early stopping, they plateaued early. So vanilla RNNs kind of failed to learn, failed to change very much over time, whereas GRUs could. Regardless, you're going to do the experiment yourself. The main message of the story here is that indeed, over these relatively long periods of time, with only about 30 word tokens, gated RNNs, in this case LSTMs, ended up performing better than the vanilla baseline on this real-world data set. So we end up, LSTMs get about 70% validation accuracy. This is by no means the state of the art in the SST2 data set, but just for the purposes of elucidation in this class, I wanted to use our models that we've been talking about on this very common, very popular data set from a very popular library, Hugging Face. So please download this and play around with it as much as you possibly can. We had a lot of design choices here, some of them to save me time, some of them just for practicality's purpose. First, these sequences are of moderate length, and usually with moderate length, LSTMs and GRUs are going to start overperforming vanilla RNNs. But if you have a shorter lengths, the gap is going to get shorter. If you have longer lengths, if your reviews or if your text is on the order of hundreds of words, then LSTMs and GRUs are going to start pulling away from vanilla RNNs in terms of the performance. We're going to see something much more similar to what we saw in example 1 a few moments ago. As always, just like the hypothetical student from the anti-example from this module, always do the experiments yourself. Never come away with anything I'm telling you thinking like we have the silver bullet. I've learned something more complicated, therefore it must be better, and we saw some examples in which it performed better than the baseline. Don't do that. Always do the experiments yourself. This train validation gap is a useful proxy just to make sure you're not overfitting. So again, these models are highly parameterized. So the more parameters you have, if you have a fixed amount of data, the riskier your training process is to overfitting. So you can always compare the validation curve, which is a solid line, against the training curve, which is this light dashed line. And you can see if these lines are kind of diverging from one another. Again, this is somewhat subjective, but it kind of is helpful as a diagnosis of potential overfitting. So, how to choose your recurrent cell. If you have short sequences, the rule of thumb is maybe RNN, like vanilla RNNs are sufficient, but maybe even simpler models than that. These RNNs are very bad. These vanilla RNNs, and certainly bags of words with only a context window, are not very good at long-range dependencies, so don't use them. If you have a moderate sequence, try GRUs. There's fewer parameters. If you have long sequences, try LSTMs. I would go a bit further and say, normally my personal rule of thumb is to use GRUs first, but the standard convention is LSTMs for long sequences. In the absence of other models we'll talk about shortly. If you're compute constrained, if you're trying to run these gated recurrent neural networks on a laptop or on a smart device or a smartwatch, for example, then GRUs might be better just because they have fewer parameters. So if you need long-term memory and computational requirements are a concern, GRUs are your model. But there are other models that have superseded a lot of the need for GRUs. These are transformers, and you might know transformers because they come up in the acronyms of very popular models these days, and they are sort of the leading edge in terms of or the computational models. But we haven't talked about the necessary component that we need on top of LSTMs, RNNs, GRUs that allow us to use transformers. That's the topic of the very next module. So we're still building our knowledge base. A quick diagnostic for you when you're running experiments. Does your validation loss plateau or flatten while training loss keeps falling or improving? This can mean overfitting, which again, reduce capacity, like change the width of your hidden vectors and your cell states, maybe add dropout, maybe add other forms of regularization. Do both losses plateau early? Then this could be underfitting. Maybe you want to increase the size or train longer. This is really the case that we saw in a few moments ago in the examples from today. Is LSTM always outperforming GRU? Then this might indicate that there's something in the task that requires fine-grained cell control. Speaking very vaguely, it's very hard to specify or diagnose where this is happening. But this can be a superficial behavior. If GRUs are outperforming LSTMs, then by all means use a GRU because they're more computationally efficient. So ethics, long-range context can amplify biased associations. If your time sequence runs not only over small measurements in time, like a cardiogram or a speech, then you might be incorporating stereotypes over very long periods of time indeed, in which biases can propagate very effectively through these cell states or through these managed hidden states in a GRU. And again, real-world data sets like text can carry all kinds of correlations, including gender-profession correlations that can be deeply remembered or amplified in gated RNNs in a way that RNNs might overwrite and forget. This is speaking very loosely. This is a risk that we have to be aware of. Memorization of sensitive attributes. The more you're able to explicitly memorize things, which is exactly what LSTMs are meant to do, the more the risk of remembering or memorizing sensitive attributes becomes a problem. So any kind of personal information in medical notes, chat logs, location traces that occur backwards in time, if they're useful to making decisions in the neural network's context, they can propagate along these cell states or managed hidden vectors, respectively, and then the privacy and the problems related to privacy come up. There are lots of ways we can mitigate against it. Differential privacy is the de facto way to do it. There is a technique we can use to apply the updates and optimization. There's stochastic gradient descent, but modified for differential privacy. This also comes with its own problems, but regardless, this is beyond the scope of this class. You're more likely to see this in a fourth year class at Dalhousie on responsible AI or in grad studies, or indeed in other resources that you can find elsewhere. So whenever you're deploying any model, really, not just RNNs, but including RNNs, ask yourself what information from the past can be weighting heavily on decisions I'm making in the present or in the future, and is it possible that some of this information can encode protected attributes or could otherwise be used to hurt or otherwise disadvantage individuals. As always, here are your quick checks. Please go ahead and do them. And small number of reading. There's a couple of links you may want to check out also. As always, thank you so much. See you next time.